Hello, my name is Nikola Samardzic, and together with my co-first author, Wei-Kang Kiao, I will present our paper, Bonsai, High Performance Adaptive Merge Tree Sorting. Our advisor is Professor Jason Kong at UCLA. Here's the outline of our talk. Let's look at sorting performance in latency per gigabyte for state-of-the-art CPU, GPU, and FPGA sorters. We list performance over a vast range of array sizes from 4 gigabytes to 100 terabytes. Lower values are better. Paradis is the fastest CPU sorter, but only considers arrays that fit into its 64 gigabyte RAM. Dashes in the table indicate no reported results. Tencent Sort uses a distributed system of CPU nodes to achieve world record results in the terabyte scale range. Here are respectively the best single GPU and distributed GPU sorters, as well as FPGA sorters. We highlight the best performing implementations for each array size in blue. The key insight is that each sorter performs well only within a specific problem size. To resolve the drawbacks of earlier implementations, we introduce Bonsai, an adaptive FPGA sorter that can use any computational and memory resources optimally. The adaptive architecture allows Bonsai to configure its sorting hardware to work well with any problem size, as illustrated in this table. For a 4 to 32 gigabyte array size, Bonsai has a minimum of 2.3x, 1.3x, and 1.2x speedup over the best designs on CPU, FPGA, and GPU respectively. Let's discuss how Bonsai achieves this. First of all, Bonsai uses merge sort because it's asymptotically optimal, both in terms of the number of compute and I/O operations. Additionally, it has predictable and sequential memory access patterns. And finally, merge sort is a stable sorting algorithm. Bonsai implements merge sort using hardware mergers and merge trees. There has been plenty of work on making these merging primitives fast. However, there is no single merge tree that works well on all hardware, and previous work did not build a complete sorter that can optimally adapt to different hardware constraints. For example, it is unclear when we should keep data on the FPGA and when we should store it back on DRAM, or maybe even to SSD storage. How much better can merge tree performance get if we double DRAM bandwidth? What about if we double DRAM capacity? Our work comprehensively explores these types of questions and implements a full sorting solution that can adapt to each of these scenarios. First, let's see how mergers and merge trees work. Hardware mergers merge two sorted input arrays. For example, the merger in the figure will merge the sorted arrays 1357 and 2468. It reads the top values from its two input streams, compares them, and outputs the smaller value, and this process repeats on every cycle. The naive merger outputs one record per cycle. To increase the merging throughput, Saito et al. Created a merger that outputs multiple records per cycle. We call a merger that merges n records per cycle an n merger. The input to the n merger are two sorted input arrays. But the new design requires that both input and output streams are formatted as n tuples. The figure shows an example of a for merger merging odd and even integers. The higher the throughput of a merger, the more on-chip resources it requires. A merge tree is a binary tree with mergers at each of its vertices. We feed the sorted arrays into the leaf mergers. The leaf nodes read their respective inputs, compare the values, and output the smaller one. We feed new values from tops of the respective input streams, and this process repeats. The merge tree allows us to merge more than two arrays concurrently. We define arity as the number of arrays the merge tree can concurrently merge. In this example, arity is equal to 8. We denote arity with the lowercase l. We can use multi-record mergers to increase the throughput of merge trees. Specifically, looking at the figure on the right, we can construct a tree that outputs 4 records per cycle if we put one for merger at the root of the tree, two mergers at the level below it, and 4 one mergers at the leaves. In general, the throughput of the tree will be equal to the throughput of the merger at its root. We denote the tree throughput with the lowercase p. So, as explained in the previous slide, the tree in this example has throughput p equals 4 and an arity of l equals 8. As an example, if we remove level 2 from the tree, the arity drops to l equals 4, while the throughput is still equal to 4. If we now change the mergers at level 1 from 2 mergers to 1 mergers, and the merger at level 0 from a 4 merger to a 2 merger, the tree throughput P drops to 2 while the arity is unchanged. Let's illustrate how merge trees can be used to sort a 64 record array. We load the first 8 records from DRAM onto the FPGA, merge them, and return the resulting 8 record sorted chunk to DRAM. And repeat. Notice that during these steps, we stream the entire input array onto the FPGA and back into DRAM. We will call each such streaming cycle between the DRAM and FPGA a merge stage. Therefore, the figure now shows the state of the sorter after the first merge stage. For the second merge stage, we merge the 8 record sorted chunks into a single sorted array. To sort even more data, we would just perform more merge stages. Now let's look at the performance of a merge tree. Specifically, what affects total sorting time? 2 things. First is the total number of merging stages required to sort. This depends solely on the arity of the tree. In the previous example, we sorted 64 records in 2 stages using a tree of arity equal to 8. 2 stages were sufficient because 8 squared equals 64. In general, the total number of stages will be the logarithm base cell of the number of records in the array n. The second factor that affects sorting time is how long a single merge stage takes. Assuming memory bandwidth is not the bottleneck, the time to perform a merge stage depends solely on the throughput of the tree P. So higher arity L means we need less merge stages, and higher throughput P means we need less time to finish each stage. Both of these are good. However, increasing either P or L it requires using limited on-chip resources, and that's bad. So this presents a trade-off. Since we cannot increase both P and L, which one is more important? Well, it depends. Different FPGA and DRAM configurations have different optimal P and L values. There are 2 reasons for this. First, as mentioned, the specific FPGA we use will limit how big P and L can be. And second, it's not worth increasing tree throughput P beyond the DRAM bandwidth. Therefore, we want to first increase tree throughput to match the bandwidth of DRAM, and then increase the tree arity as much as possible. The sorting time is equal to the time it takes to finish one stage multiplied by the total number of stages. The part in green is the total number of stages, and the part in blue is the time to execute a single stage. It is equal to the number of bytes in the array divided by the throughput of the merging stage. This throughput is equal to the minimum of the throughput of the merge tree and the DRAM bandwidth at beta DRAM. In summary, the optimizer takes the available FPGA resources, DRAM bandwidth, and input array size and record width as inputs, and outputs the optimized merge tree design. Formally, the optimizer solves a constraint optimization problem. Now let's look at DRAM scale and SSD scale optimal Bonsai designs. First, consider DRAM scale sorting. This graph shows the sorting time for a 16 gigabyte array as a function of DRAM bandwidth. Lower values are better. The blue line shows Bonsai's performance predicted by our optimizer. The 4 blue diamonds show Bonsai's measured performance. We also include 3 state-of-the-art sorters on FPGA, GPU, and CPU. The yellow line shows the time required to stream the data onto the FPGA and back to DRAM. This yellow line gives an IO lower bound. We see that the 3 other implementations are optimized to work only with a specific bandwidth. In contrast, Bonsai adapts to different memory bandwidths. Indeed, the 4 listed Bonsai results all use different merge trees. Finally, no matter how fast future memory bandwidth gets, the optimal Bonsai design will always be at most a fixed constant factor worse than the IO lower bound. The Bonsai design at 32 gigabytes per second is optimal for the AWS F1 FPGA instance. It uses a single P equals 32 and L equals 64 tree. Sorting terabytes of data introduces a memory hierarchy consisting of fast but small DRAM and slow but big SSD storage. We will sort in 2 separate phases. In the first DRAM phase, we will create many DRAM size sorted chunks. In the second SSD phase, we will merge these chunks into a single sorted array. We use tree pipelining for the first phase. Tree pipelining uses multiple merge trees to sort a batch of arrays. The pipeline keeps the I/O bus busy at all times, making pipelining ideal for slow SSD storage I/O. To understand how pipelining achieves this, let's first explain how it works. In this figure, yellow triangles stand for merge trees. The square on the bottom left of the figure represents the first array in the batch. We stream this first array onto DRAM bank 1. The number on the array indicates the size of the sorted chunks in the array. As the array is not sorted, the sorted chunk size is equal to 1. We stream the first array through the first tree in the pipeline and then store it into bank 2. Assuming the arity of the tree is L, the first array will now have L record sorted chunks. Synchronously with this first merge stage, we stream the second array into bank 1. We then merge the two arrays through their respective trees, while a third array is streamed into the bank. This continues until all the arrays in the batch are sorted. To reiterate, in tree pipelining, the last tree in the pipeline outputs a sorted array during every stage. This setup keeps the I/O bus busy and minimizes the impact of slow I/O. After the first phase, the array is organized into many DRAM-sized sorted chunks. This means the DRAM is too small to mask the slow SSD bandwidth during the remaining merge stages. As we cannot rely on DRAM bandwidth to get good performance in the second phase, we can reduce sorting time only by minimizing the remaining number of merge stages. To that end, we reconfigure the FPGA to run a single high-arity merge tree during the second phase. We then use this tree to recursively merge the DRAM-sized sorted chunks. For example, using a tree of arity L equals 256, we can merge up to 4,000 terabytes of data in only 2 stages within the second SSD phase.
Hi, this is Weikang, and now let me show you the microarchitecture of our Bonsai, as well as the implementation details. We implement the single AMT system on AWS F1. The merge tree is built using multi-record mergers, as presented before. We can fix our accesses to 1, 2, and 4 DRAM banks to measure different off-chip memory bandwidth configuration. To make full use of the DRAM bandwidth, each leaf is equipped with a buffer that is able to hold multiple read batches. The X interface between the sorting kernel and the DRAM controller is always 512-bit, regardless of the record width. The unpacker will extract one record from the 512-bit FIFO every cycle. And on the other side, the packer will concatenate the output of the merge tree into 512-bit wide data. Next, we want to specifically present 2 important considerations that enable our design to work efficiently. The first is data loader. To access off-chip memory at its peak bandwidth, the data is loaded in 1 to 4 kilobyte batches in sequential for each leaf node. The input buffers should be large enough to hold multiple outstanding batches. Besides, to make sure the DRAM access of the leaf nodes adapt to the input data skew, the data loader needs to keep track of the buffer status in a round-robin fashion. So whenever an input buffer is full, that indicates its corresponding leaf node is not active, and the data loader will skip fetching data for this node and allocates more bandwidth for the other active nodes. The second consideration is how to efficiently reset the merge tree. In fact, the merge tree's control state needs to be reset before it can merge another trunk of new input data. This reset is repeated hundreds of thousands of times, especially at the initial stages where each merge trunk is very small. That means the reset scheme must be efficient. On the other hand, global reset to the entire tree will have a huge fan-out problem. So in our design, we use a reserved terminal record that is propagated through the data path to flush the merge tree state. For example, we use 0 when sorting positive integers. That's why we see this 0 append and the 0 filters here. So in this way, we avoid the global reset and only have 1 extra cycle latency. Next, we will show the experimental results. We run our experiments on the Amazon AWS F1 platform, which is equipped with a single 16 nanometer FPGA and 64 gigabyte device DRAM. The DRAM has 4 banks. Each bank has roughly 8 gigabytes per second concurrent read and write bandwidth. The main benchmark we used is 32-bit integers generated uniformly at random. We also use 16-byte records to check the scalability of the record width. Our designs can run at 250 MHz or even higher frequencies. We ran a lot of experiments with different DRAM configurations and different merge trees correspondingly. For example, all the AMTs with a throughput of p equal to 4 and p equal to 8 correspond to the single DRAM bank configuration. And AMTs with p equal to 16 and p equal to 32 correspond to the configuration of 2 DRAM banks and 4 DRAM banks, respectively. Now let's come back to the question of how to choose the right P and L given the FPGA and the DRAM configuration. The first observation is that when merge trees have the same throughput, the greater LTL usually has better or equal performance. On the other hand, when merge trees have the same LTL, the higher throughput gives better performance as long as DRAM bandwidth is not saturated. So as a result, the strategy of choosing optimized single AMT configuration is always as below. First, we choose a minimum tree throughput P that saturates the DRAM bandwidth. Then we choose a maximum L that on-chip resources allows. The best performing design is AMT P equal to 32, L equal to 64, which corresponds to the case where all of the 4 DRAM banks are presented. The resource utilization is also attached. Please note that although L can be even larger, here we limit L to be 64 since design with more leaves have lower frequencies due to the FPGA routing congestions. We also compare our optimized DRAM sorter with state-of-the-art CPU, GPU, and FPGA sorters. And as we can see, our sorter always has the best performance across the datasets with a size of 4 to 32 gigabytes. We also list our projected SSD sorter performance, which contains 2 different phases as mentioned before. As we can see, the reprogramming time is negligible when compared with the total sorting time, showing the idea of 2 phases works. With the systematic approach we proposed, we can now form a big picture of how the performance looks like when the size of datasets ranges from gigabyte to terabyte scale using a single FPGA-based merge sorter. As we can see, the performance decreases at 4 distinct points. The first point comes when there is one more merge stage in DRAM sorter. The second point comes when we switch from DRAM sorters to SSD sorters to accommodate a larger dataset. The third and fourth points comes when there are more merge stages in SSD sorter as the datasets becomes even larger. We also measure the scalability in record width of our design by comparing the 32-bit record and the 16-byte records. We find that when targeting the same throughput, mergers for 16-byte records have very similar or even less on-chip resources, which indicates our designs have good scalability for different record widths. So in summary, in this work, we propose a novel adaptive merge tree architecture that adapts sorter designs to the available chip resources and off-chip memory bandwidth. Based on that, we built Bonsai, a complete sorting solution that uses comprehensive models to optimize sorting performance. With Bonsai, we achieve state-of-the-art DRAM sorter performance on AWS, and we also extend our analysis across different memory hierarchies. That concludes our presentation. Thank you for listening.